Thanks. There's even a flash page for that. So welcome. So let me see whether I can get rid of this. I guess not for long, but oh no, now it's broken. I'm sorry about it. The full slideshow, I guess. Yeah, doing Starknet protocols in Quint. So the point here is about modeling and analyzing the protocols. I'm reiterating on the complexity of this system, on the three-body problem that Adi talked about. So we have Ethereum, we have Starknet, we have provers in between. And the moment we're going to, Ethereum is already a distributed system, Starknet is going to decentralized. So what we're going to have here is a distributed system of distributed systems. So already distributed systems are very hard to understand and to get right, and having more of them is very complicated. It's very easy to think wrong and to include bugs. So the two main concerns that we are trying to address in this work that we have done over the last month is the first thing is, can we make sure that there are no design bugs before having implemented everything, right? Development is going on right now, and we don't want to wait until the very end, until everything is here, to figure out we did something wrong. And the second thing is that you've seen a lot of people here, so there's a lot of teams working together, there's a lot of interaction, and we need to make sure that these people are actually doing work that interacts, that can work together, right? So the second big goal is that these specifications are unambiguous, and these are the big goals. And to explain why this is not obvious that we can reach this goal, I would like to sort of show a little bit a typical design flow of projects that we have seen. So typically what you start up with is, of course, with an idea, and then you start to write things, and typically people start to write APIs, data structures that give some code fragments to describe some algorithmic ideas. But these sort of documents, they focus very much on the logical part of the local part of code that runs on a single machine. And then the question comes when we go towards distributed systems to think about, if this code runs on multiple machines, how is this interacting? And this work typically happens by scratching our heads, we have discussions, we do drawings, but we are always sort of trying to figure out, did we miss some corner cases? Do we have sort of all our bases covered? And sort of at this point, I would highlight that we have a little bit an issue here. Because this is the point where there is a lot of complexity. You have asynchrony, you have the distributed systems, you have partial failures, you have concurrency, you have different scenarios, and all this sort of is derived in discussions, and then it's stored in brains typically, and we don't have the means to write them down easily, not as similar to how we write down sequential programs. And because we have these issues and it's only stored ambiguously in brains, we suffer later on in the process. In the coding, we suffer because we're not sure whether we have eliminated all design bugs, we are not sure whether we have eliminated the ambiguity, and also we have the problem that the people who do the implementations are not the brains that have talked about the problems in the first place. And so this is what we're trying to address here. And yeah, we use Quint for that. So Quint is executable, it's unambiguous, and it surfaces problems early. So let's quickly step out a bit and let's see what Quint is. So Quint is a modern executable specification language that we have developed at the Informal System. So it's executable compared to Markdown or English. You can actually type check, name check your specification. You can execute them, so it's a simulator that actually lets you run your specifications. It's abstract in the meaning that you decide the level of detail that you want to have. So you don't have to implement everything to start thinking and to start reasoning about the system. And it's modern. So in contrast to specification languages that have been developed in the past, that often had a very weird syntax, math-like syntax, the syntax is very familiar with modern languages, and the experience in writing in the editors is very smooth. So what has changed now? So the process now is a little bit different. So we start with writing Quint specifications. Of course, we define the data structures that we need to express our protocols. We define functions that eventually should be implemented. This is sort of the interface also to the engineers. But then we already move into the realm of distributed systems. So we can define state machines of distributed systems. And then, instead of scratching our heads, we are actually letting the tool doing a lot of the analysis for us. So we automate the search for design issues. We can, instead of drawing sort of executions or things like this on the board, we can actually encode these interesting scenarios, and Quint is doing the thinking for us. And the result is that down the line, we work with much higher confidence in the later stages. So having said this, I would like to give you a little bit a taste of the language and what it can do for you. And I ask you to please don't try to understand everything which comes on the following slides. I will highlight what is sort of important and interesting here. So it's a state. You can encode state machines. So you define an initial state, and you can define transitions that bring you from one state to another. That looks like this. Again, don't try to understand everything here. I think the most important part is here below the step that there is the keyword any, and then follow up by like 4 different actions. So this defines all possible steps that could happen next. So you could, for example, for the initial state, you do a add registration step, and in the next step you do a add L2 block step. So all possible, it goes all possible ways in which steps can happen next. This is just sort of the highest level. There's a lot of code behind for this, but in the end, what you can do, you can say Quint run, and it's going to do a random simulation of your project here. And here, if you would scroll up, you would see a sequence of states that sort of you came up here, and this gives you sort of an example execution of your system. The next thing is you want to reason about correctness. So you want to reason about the states that you can reach and the states that you cannot reach. And the important property here is invariance. These are properties that should always hold. Again, don't make too much, try to read everything here. The important thing to observe here is there is like a point here. So this the keyword implies. So these are logical connectives. You can write logical formulas here. There is a for all, so you can have quantification over sets. And basically, this is a property which relates proofs from L2 blocks that are accepted on L1, and you just want to make sure that this property always holds, no matter what happens. And then you ask Quint, so is it the case that this always holds? And it does this. So it does like random simulation of, I don't know, 10,000, 100,000 of executions, and here reports back that it didn't find a violation. So that's here. Here in this line. Here in this line. And it just gives you again an example execution. You can scroll up and look sort of how just one of these executions look like. And also it's random, right? So the next time you run Quint, you might get a different example execution, but there is the seed here, so you can use the seed to get to the same executions again. And then sort of there's this sort of typical design artifacts where we draw like messages, how messages are sent from one node to another node, and try to convince ourselves that sort of the system is doing what it's supposed to do, and sort of this is the equivalent in Quint. So here we can actually describe runs of a system. So here we have like we have an initial state, and then sort of with the then keyword you put actions on top one on the other, and then sort of at the end you expect that a certain property is holding. And actually, oops, I'm sorry. And actually, the the thing, sort of this first action here is not an action, but it's actually a run. So it's again a sequence of actions that in this case involves adding a registration, adding a block to L1, adding a block to L2. So there's like the whole system sort of behavior is described here. So the concept here that is called tests, and what you can then do is you ask Quint, can you check all the tests? And that's what is the output here. Also what you see here is that there are like 3 different tests. In just the last line here is the one that's given on the slide, and it actually ran 10,000 tests because there is non-determinism hidden somewhere in this action, in these actions, and it tries to search all the non-determinism for all possible actions that you can have. And then perhaps you are too lazy to do these scenarios, or perhaps you find you're not sure whether a certain state is reachable at all, and then basically you can even ask Quint to generate the scenarios for you. So we call this witness, and witnesses are basically formulas, again, don't try to make sense out of this, that describe an interesting state. So for example, we want to, this is one witness, is one where we want to reach a certain state where a proof is accepted on L1 that corresponds to a reset, to a fork on L2. So there's the formula for that, but you're not sure sort of what steps you need to actually end up there. And then you ask Quint, and it comes up with a scenario. So you can actually then go back and understand all the steps that happened that you reached that step. So this is what we did for the Starknet protocols, also for the protocols that were mentioned in the talk before. So we modeled and analyzed them, also for Malachite consensus, which sort of address the concerns that we have raised here for the first 2 points. To give you some idea, so for the validator upset alone, this is sort of the protocol that lives between L1 and L2. We have 14 invariants and 18 witnesses that describes interesting states and properties. And so this gives us a very good and precise understanding of the protocol. And all this is done in our Quint language. There's a new web page. Check it out and play with it. And I think I'll stop here. So if you're interested to analyze your protocols with Quint, come to us. We are happy to help you. And also we are hiring, so visit our web pages. Thanks. The question is what we can do, whether the difference between what we can do with Quint and with an interactive theorem prover. The point with interactive theorem provers is you actually have to write the proofs, right? So you have to put a lot of understanding in figuring out like why a certain invariant holds, right? And Quint is just searching the state space and doing this automatically. So you don't have to figure out the reason. It's just the tool who is searching for that. So we have also a link to Appalachia, which is a model checker. There you can get more complete results. You can also look with so inductive invariance is something also we are looking into, which is sort of like gives a one-step verification problem. So there are different things you can approach. Okay, thanks.